In this video, we are going to talk about the Schwarz Christoffel transformation. This is our overview slide, which we'll spend about 5 or 10 minutes on before going over all of the material in more detail and with an example. The first thing to talk about is what is the Schwarz Christoffel transformation? Well, it's a transformation f of z, and it goes from the z-plane to the w-plane. So it's a transformation w equals f of z that maps the whole x-axis. That's the x-axis here in the z-plane. So it's the real axis of the complex plane onto a polygon of n sides, where x1, x2, x3 up to x of n minus 1, that's over here in the z-plane. These are these points on the x-axis, and also xn equals infinity, are the points on the axis whose images are going to be the vertices of the polygon. So x1, for example, will map to this vertice w1. x2 will map to the vertice w2. x3 maps to the vertice w3. And then x of infinity comes back to wn. The vertices of the polygon are then the endpoints w sub j, as we just discussed, and w infinity at infinity. To approach this problem, we look at how the function f should change as we hit each vertice. So in other words, the function f should be such that the argument of f prime of z, the argument being the angle, jumps from one constant value to another at the points of these vertices, or the x sub 1, x sub 2, that corresponds to the vertices. So in other words, our argument should be constant, but the moment we hit a vertex, or one of these z's, f of x sub j, one of these points that maps to a vertice, then we should get a change to another constant value until we hit the next vertice. The proposed f prime of z then is equal to a times z minus x1 raised to the minus k1 exponent, z minus x2 raised to the minus k2 exponent, all the way to z minus x sub n minus 1 raised to the minus k to the n minus 1 exponent. And what this exponent tells us then, that has to do with the angle that needs to change as we hit x2. So in other words, when we hit x2, that corresponds to the vertice w2. When we're going from w1 to w2, we're at this angle here. We're on this line. But then as we hit w2, we need to rotate by k2 pi degrees, or radians, to get our next side of our polynomial until we get to k3. Then we're going to rotate by k3 pi. And so these k's are these angles times pi, or the coefficient times pi will give us the angle we need to rotate by. We will go through this in more detail in the main part of our video, and we are going to be using this relationship here. When you multiply a complex number by a second complex number, then this first complex number, what happens is it's rotated by the angle of the second complex number. Once we have this formula for the derivative, then we need to integrate in order to get our f of z. There's several notes we have here about this, setting this up. Also, we will be using this formula here for our exponent when we work on this, as well as something called the beta function, because some integrals of this form are difficult to integrate, but we're going to leave this in this form, that this integral is equal to bp of q. And we will do an example of the equilateral triangle. The final thing we will do is look at some limitations of the Schwarz Christoffel transformation. That wraps up our overview, so let's start by looking again, take a closer look at the mapping of the real axis onto a polygon. Since we're going to be talking about f prime of z, we're going to look at some of these tangent lines. So here is our function f of z, which maps from the z-plane to the w-plane. We have a curve c that gets mapped to the curve f of c, and the point z naught that gets mapped to w naught. So this tangent line here, that's going to be the unit vector, which is tangent to the arc c at a point z naught. And we call that tangent vector t. Then we also have tau over here That's the unit vector tangent to the image of f of c at the corresponding point w naught, that z naught gets mapped to. We're going to assume that f is analytic at z naught and f prime of z is defined and not equal to 0. We are going to let c be parameterized as z of t for t going between a and b. Then f of c is equal to f of z of t for t going between a and b. And now we're ready to talk about the derivative. Now when we take the derivative of f of z of t with respect to t, we need to use the chain rule. So we're going to have w prime of t is equal to f prime of z of t times the derivative of what's inside, z prime of t. Which means that w prime at t naught is going to equal to f prime z at t naught times z prime at t naught. Now you have three complex numbers. This w prime of t naught is a complex number, and then you have a product of two complex numbers here, f prime of z of t naught, and then this complex number z prime of t naught. Each of these complex numbers, remember, you can write it in exponential form, so you can talk about its radius and you can talk about its angle. And the angle, if you recall, we call it the argument. So now we can talk about the argument of w prime at t naught and the argument of f prime z of t naught and the argument of z prime of t naught. And as I had mentioned in our overview, when you multiply two complex numbers, what you get are the radii are multiplied together, and then you get e to the I, and then the angles are added. So here the arguments are added because the two complex numbers are multiplied. And expressed in terms of our t and our tau, that means the argument of tau now is equal to the argument of f prime at z naught plus the argument of t. Remember, on our Schwarz Christoffel, we're mapping the real axis here. So in this case, t, the angle is equal to 0 because we're on the real axis. So for c on the x-axis, on the real axis, then the argument of tau is just simply the argument of f prime at z naught. Since this is equal to 0, the argument of t is equal to 0. I've summarized all of this here. We wrote f of c is equal to f z of t. When we take the derivative, we need to use the chain rule. And then when we take the argument, when we have the product of two complex numbers, we add their angles. And then we have this result that argument of tau is equal to argument f prime of z naught plus arg of t. And if c is a segment on the real axis, then our angle is equal to 0. This t will be at arg of t is 0, so that arg of tau is equal to arg of f prime of x. And now we want to construct that transformation w equals f of z that maps the whole x-axis onto a polygon of n sides, where x1, x2, x3 up to x of n minus 1 and xn equals infinity are the points on the axis whose images will be the vertices of the polygon. And then also our x1, x2 up to xn minus 1 there in order of increasing or going more and more to the right on the real axis. The vertices of the polygon are the endpoints w sub j, which corresponds to f of x sub j. And wn is equal to f at infinity. And again, the function f should be such that the argument f prime of z, in other words, when we look at how the angle changes, the angle is going to be constant until, so it jumps from one constant to another, and it jumps at the points z equals x of j, or corresponding to the vertices. So that's where our angle is constant, but then it jumps at the next vertice. And the function we're going to consider is f prime of z is equal to a times z minus x1, this x1 is over here, to the minus k1, and k1 is about the angle we need to transition to at the first vertice, z minus x2 to the minus k2, and this k2 is about the angle as we meet this second vertice up to z minus x of n minus 1 raised to the minus k n minus 1, where a is a complex number, it's a scaling factor, and k sub j are all real numbers. I've put my formula for f prime of z up here. Now, just as we had this rule here that said when we multiplied two complex numbers, our arguments add, here we have n complex numbers, the x1, x2 up to xn minus 1. A is also a complex number. So n complex numbers. So when we take the argument of f prime of z, we're going to add the n arguments. So the argument of a1, the argument of this factor here. The minus k1 becomes a constant multiplier times the argument of z minus x1. Here we take the argument of this next factor. The minus k2 becomes a multiplier arg of z minus x2 all the way up to minus kn minus 1 argument of z minus xn minus 1. And I just have notes here on how I converted from here to the argument here. So again, if we have z minus x1, if that's the complex number r e to the I theta, then z minus x1 to the minus k1, when we take r e to the I k theta, then the arg of z minus x1 is equal to minus k theta. We're going to consider what happens as we move along the real axis, and we're going to start when we're out here less than x1. So let's start. When z is equal to some number on the x-axis, some x, and x is less than x1, so we're over here, then z minus x1 points in the negative direction. Remember, when you have vector a minus b, b is your starting point, a is your ending point. So if z is to the left of x1, and you're starting at x1, and then you're going to z, you're pointing in the negative direction. And that's opposite of our orientation for c, our curve, which is going to the right. Which means all of these arguments here, the z minus x1, z minus x2, all the way up to z minus x of n, is 180 degrees than our positive direction. So in other words, the argument is equal to pi because we're going in the negative direction. Again, it's like 180 degrees opposite of c. So our argument then for all of these is equal to pi. So we're constant over here before we hit x1. Now let's consider what happens once we pass x1 and we're between x1 and x2. So z is equal to x between x1 and x2 over here. Now consider z minus x1. So this is our starting point, x1. When we point towards z, we're pointing in the positive direction, which is the same direction as c. So the argument of z minus x1 is 0. Looking at our formula up here now then, this argument of z minus x1, this goes away. This becomes 0. Before over here, before we hit x1, when we were less than x1, remember this argument of z minus x1 was equal to pi. And so it contributed something to the argument of f prime of z. So once we hit x1, you can see that this then changes the angle of our f prime of z. The other thing to note is all other arguments, they are still pi. So for example, let's look at the argument for z minus x2, and I'm just going to put this, box this in yellow just to highlight. We're looking at z minus x2. Now remember, we're looking when z is between x1 and x2. So z is somewhere over here. So z minus x2. And remember, when we have a vector minus a vector, this vector, the second vector, is the starting point. So we're starting at x2 and we're going to z. So in other words, starting at x2 and going to z, we're going to be going in the opposite direction as c. So in other words, we're at 180 radians or 180 degrees. I'm sorry, 180 degrees or pi radians. So in other words, I'm going to write this a different way. The argument of f prime of z, we're no longer subtracting this k1 pi. So argument of f prime of z increases abruptly by an angle of k1 pi as z moves to the right through the point z equals x1. So that's what this is. Similarly, when you come to x2, when you're looking between x2 and x3, now x2, this argument will be equal to 0, but all the other x3, x4, etc., the ones to the right of x2, those will also be equal to pi. So similarly, the argument f prime of z jumps in value by k2 pi as z passes through x2, etc. So I have some of those key points summarized here. This was our f prime of z that we proposed to do this mapping from the real axis to the polygon. And then what we looked at is what the angle then at f prime of z looks like using this kind of this formula here to guide us. Like when we have the multiplication of two complex numbers, we add their arguments. So here we have n complex numbers, so we're going to take argument of a, and then we add all their arguments, except because of this minus k1, it becomes we subtract all these arguments. Then we talked about what happens as we travel from the negative infinity along the x-axis. So before we hit x1, we said that the argument of z minus x1 is equal to pi, and actually the argument of everything to the right of x1 will be equal to pi. But the moment we hit x1, and now our x value is between x1 and x2, then the argument of z minus x1 becomes 0, and all the other arguments remain pi. So what happens to the argument f prime of z is our angle then increases by k1 times pi, because now we no longer subtract as we did when we were less than x1. And this is how we're going to get these angles here. So before x1 will be at some constant angle. As we hit x1, we're going to have to change our angle now, and it changes by minus k1 times pi. I'm sorry, k1 times pi, there's no minus. As we hit x2, our angle now changes by k2 times pi. And this continues until we get our polygon. And just a word of advice, these ideas here, when we find the argument of z minus x2 or z minus x1 or z minus xn, we're going to be using those often when we're doing examples. So make sure that you understand how it works and that you remember this. And we have some notes here. Then the unit vector tau is constant in direction as z moves from x of j minus 1 to x of j. The point w thus moves in that fixed direction along a straight line, and the direction of tau changes abruptly by an angle k sub j pi at the image point w sub j of x of j. These angles, k sub j pi, are the exterior angles of the polygon described by the point w. We have this condition that all of our k's will equal to 2. And is there anything else? And this is how we derive this condition, which I won't go through, but I'll let you look at if you're interested. And now that we have our formula, or we've considered our formula for f prime of z, we integrate to get our formula for f of z. And there are many points, like your book goes through this, which I will not go through the derivation or the different points on here, but there are some notes that we should consider. So here I have our notes from our previous slide with f prime of z, and we want this function here, this a times z minus x1 to the minus k1, z minus x2 to the minus k2 up to z minus xn minus 1 to the minus kn minus 1 to be the derivative of a function that maps the x-axis to the polygon. F prime of z is analytic everywhere in the half plane, y greater than 0, except at the n minus 1 branch points, x sub j. And this is shown in your textbook then. We can then say that w is equal to f of z equals a integral from z naught to z s minus x1 to the minus k1, s minus x2 to the minus k2, up to s minus xn to the minus kn minus 1 ds. So s is just our variable of integration plus b. Now a is our scaling function, b is just a positional function like a translation function. So we suppose the constants x sub j and k sub j are such that the sides of the polygon do not cross, so that the polygon is a simple closed contour. As the point Z describes the x-axis in the positive direction, its image W describes the polygon in the positive sense, so in the counterclockwise. The complex constant A is a scaling factor, the complex constant B is a positioning term, which means we can choose A equal to 1 and B equal to 0, and we will get a polygon P prime, which is similar to P. Here's our Schwarz Christoffel transformation. Here's our f prime of z, and some other notes that are going to be useful as we do our example. First, the k1, k2 up to kn plus 1, actually not kn, right? Just kn plus 1 should equal to 2. 3 of the real numbers, x sub j, can be chosen arbitrarily. Again, we can choose A to be equal to 1 and B equal to 0, and we'll get a polygon that's similar. It might be scaled a little differently, and it might be translated somewhere differently in the W plane. We'll also be using this beta function because many of the integrals we'll get are going to be of this form, which is integral from 0 to 1, t raised to the p minus 1 times 1 minus t to the q minus 1 dt. And we will leave, whenever we have an integral of this form, we will just leave it as b of p comma q, or beta pq. And p and q are real numbers. This last formula we will be using, this is z minus x sub j raised to the minus k. This should be a sub j, but my software didn't let me write that. So let me just do this. Z minus x sub j all raised to the k sub j, and we can rewrite this, so taking the exponent and the log of z minus x sub j, and also taking this minus kj down as a multiplier. Then that's equal to the exponent of minus kj using our definition of log from chapter, I think it was 3. This is going to be the natural log of absolute value of z minus x sub j plus I times theta j, which is implies then our z minus x sub j to the kj is equal to the magnitude of our vector z minus x sub j to the minus kj times the exponent of minus I times kj times theta j, where theta j is the argument of z minus x sub j, and we'll look at this more carefully in a moment. So we're just going to go directly when we're doing this. We're not going to look at the derivation, but we're going to use this formula from this expression is equal to this expression. And in some ways, I look at this and I say, well, this sort of separates out the magnitude of this vector from the angle of the vector. I have some of the notes over here for you, and our first example is the equilateral triangle with z naught equals to 1. And here is our picture that we'll be using. We're going along the z-axis. We'll let x1 equal to -1, x2 equal to 1, and then our equilateral triangle, we're going to place it so one of the vertices is on 0, and then and that's W2, so x2 or 1 gets mapped to W2. This x1, which is -1, gets mapped to W1, and then our x sub n or x infinity gets mapped to W3. I'm going to note that here, x1 is -1, x2 is 1, x3 is infinity, and also you notice then every time we go through, we're going to make a turn of 2/3 pi. So k1, k2, k3 is equal to 2/3. So I know the angle inside the triangle is pi over 3, but think it's how much you're turning. So when you're coming down here at W1, and I extended the side of W1 below the axis over here, to make the turn to get to the second side over here that's along this axis, you need to make a turn of 2 pi over 3. So it's the exterior angle that you're looking at. And hence our k1, k2, k3 is equal to 2/3. We're going to let a1 equal to 1, b equals to 0. That now gives us f prime of z is equal to z minus our -1, so z plus 1 to the minus 2/3, and then z minus 1 to the minus 2/3. So this is our f prime of z. So w is going to be equal to, somewhere I had that z naught is equal to 1. So it's going to be equal to the integral 1 to z s plus 1 to the minus 2/3 s minus 1 to the minus 2/3 ds. The other thing we're going to note is w of x1 is equal to w1, w of x2 is equal to w2, and w of x3 is equal to w3. So we can see w of x2 is equal to w2. So in other words, w of x2, that's w of 1, is equal to this w2, which is just equal to 0. So that one's easy. Unfortunately, they didn't tell us what this b point is, or the length of this b. I'm going to note that over here. I'm just going to move that here so we can make some space to consider w of x1, x1 is negative 1, is equal to w1, which is up here. Now, looking at this integral, we're going to use this formula here to transform this integral so we can solve it, so we can integrate it. So what we have then for this first term, this is s plus 1, or s minus 1, because it actually came from this x1, which is minus 1, raised to the 2/3. According to this formula, and we're going to skip the derivation and go straight to here, that's equal to the absolute value of z plus 1 to the minus 2/3 e to the minus ik, so that's minus 2/3 I, times theta j, where theta j is the argument of z minus x of j. And this is what we were talking about a little bit earlier in our video. We were talking about the argument then is equal to 0 because z minus x1, when we're between x1 and x2, so some value, let's say z over here, or x over here, then z minus x1, that means x1 is our starting point. Our arrow, or our direction of z minus x1 is in the positive direction, which is in the same direction as c. So that means this argument is equal to 0. So I have that theta j is equal to 0 here. So e to the 0 is equal to 1. So what I'm left with is absolute value of z plus 1 to the minus 2/3. So that's this first factor over here, the s plus 1, or z minus negative 1. For my next factor, that's my s minus 1 to the 2/3. So z minus 1 to the 2/3. Plugging then into this formula, I get z minus 1 to the 2/3 exp, the minus 2 over 3i times, and in this case, again, let's go back up here to our drawing. Z is between, or x is between x1 and x2. So when we're looking at the phase of z minus 1, so in other words, we're coming from 1, that's our starting point, and we're going to x. So we're going in the direction opposite of c. So our phase, or our argument, is going to be equal to pi. So this then becomes, there's one other thing to know. So when z is between negative 1 and 1, the absolute value of z minus 1 is simply equal to 1 minus x. So that's how this transformation came about, just because we're using the fact that we're on the integral, or we're on the interval, sorry, between z is between negative 1 and 1. So then we get this gets converted to 1 minus x to the minus 2/3 e to the minus 2/3 I pi. So what this gives us is our w of x of 1, which is equal to w1 now, because we're looking for w1, is integral from 1 to negative 1. We have our x plus 1 to the 2/3. And on the interval between negative 1 and 1, this x plus 1 absolute value becomes x plus 1 to the minus 2/3. This is our 1 minus x to the minus 2/3 exponent of minus 2/3 pi I. We use the fact that, actually the next thing we do is we multiply these two together. We get, what do we have? An x, a minus x, we have a positive 1, and we have a minus x squared. So that is in the denominator. We use the fact that this is a symmetric function. So we have the 2, and we take out our exponent over here. Substituting x equals t to the 1/2, then dx is equal to 1/2 t to the minus 1/2. We can convert this over so that it looks like our beta function, which is over here. So rather than integrate this, we're going to leave this in the form of b of 1/2 and q minus 1. So that would also be 1/3. So yeah, 1/3. So that means W1 then is equal to our exponent, pi I over 3 times beta of 1/2, 1/3. Finally, we can look at W of x3. Remember, x3 is equal to infinity, so W of infinity is equal to this point here, W3. And we start by using the same formula that we used in the previous examples. So that W3 now will be the integral from 1 to infinity. Where's our formula? Our x plus 1 to the minus 2/3, our s minus 1 to the minus 2/3 dx. And that will be the integral from 1 to infinity, dx over x squared minus 1 to the 2/3. Unfortunately, we can't use our beta function here, but there is something we know about W3. Looking at our drawing of our equilateral triangle, you would expect that this point here, B, will be equal to the length of W1 to W2. So we want to use this previous result to help us with W3. And what we are going to do to use the previous results, instead of integrating now from 1 to infinity, we're going to integrate from negative infinity up to 1. That'll capture our previous results. So we're going to break up then this integral into two parts, from negative infinity to minus 1, that's over here, and then our integral from minus 1 to 1 over here. Plugging in our x plus 1 to the minus 2/3 as a complex number into our formula, that gives us the magnitude of x plus 1 to the minus 2/3 times our exponent here. But we'll look at the exponent in just a minute. But we also have our x minus 1, the absolute value of x minus 1 to the 2/3. So we kind of combine those two factors, and then times our exponent. So let's look at our exponent, where we're going to have minus I times k. So in both cases, for x plus 1 and x minus 1, our k is 2/3. So we're going to have minus 2/3 I. And now we need to figure out our theta j, our argument for z minus x sub j. For this integral, our values of x are going to range between -1 and 1. So I'm going to mark that on my graph here. Somewhere between -1 and 1 is my value of x as I integrate between these limits. So now the argument of this first factor, x plus 1 is equal to x minus -1. So our argument of this vector here, so -1, we start at -1 and we go towards x. So -1 towards x, that's the positive direction. That's the same direction as our curve, as we go along the x-axis. This is the positive direction, so the argument is equal to 0. Now let's look at this argument of x minus 1. So we start at 1 and we go towards x. So on our graph, we're going to start at 1. I'm going to do this one in green. Start at 1 and we go towards x. So now you can see we're going in the negative direction, which is 180 degrees from our positive orientation. So that means our argument is 180, or pi radians. And now when I write my expression over here, I have my absolute value of x plus 1, absolute value of x minus 1. All of that is to the 2/3. And now for my two exponents, my exponent for my x plus 1, well, that's exponent of I times k times my argument, but my argument is 0, so this just becomes exponent of 0, which is just 1. And then the argument for x minus 1, so we're going to have exp minus I 2/3, so here's our minus 2/3 I, and then times our argument, theta j, so that's pi. So you can see that's exactly what we have for our first term. Next, we're going to integrate when x varies between -1 and negative infinity. In other words, x is less than -1. So I'm going to mark that over here, some value of x. Our values of our x are less than -1. So let's look at our argument of x minus -1. So argument of x minus -1. So our starting point is -1 and we're going towards x. We're starting at -1, going towards x. You can see now our direction is negative, which means our argument is equal to pi. It's 180 degrees or pi radians from the positive direction. Now let's look at the argument of x minus 1. So we're starting at 1 and we're going towards x. So starting at 1, going towards x. Again, our direction is negative, which means our angle, our argument, is going to equal to pi. So I'm going to now write out our factors. We have our x plus 1 and our x minus 1 to the 2/3. Now our arguments now for each of these two. For x plus 1, that's exp minus 2/3 pi I. And then here, our x minus 1, we get our e to the minus I 2/3 times pi. So these add together and we get this expression here. Absolute value of x plus 1, absolute value of x minus 1, all raised to the 2/3 times exponent, adding these two together, minus 4/3 pi I. And as I mentioned, W3, because this length of W3 is B, and the length here between W1 and W2 is B, we're going to relate, we wanted to relate W3 to W1, and it turns out this expression here is exactly what we have for W1, and you can go back and look at it if you'd like. But this is W1 here, and then we have this remainder of this expression. This is our, we're going to pull out our constant, our exp minus 4/3 pi I, and then we have the integral from -1 to negative infinity, x plus 1, x minus 1, all to the minus 2/3 dx. When we saw this equation, when we saw for W3, we're going to get then W3 is equal to, here, this W1 was b to the beta function, 1/2 1/3 e to the pi over 3i. Again, this is W1, which we had worked out previously. And then we have this expression here, this part, this minus 1 to infinity. This was our original W3, which is over here. So this is then W3 times our e to the minus pi over 3i, which implies that W3 is equal to the beta 1/2 1/3 e to the pi over 3i. Okay, so now we've talked about the Schwarz Christoffel transformation, and this example that we did here, it was much longer than these 3 steps I showed you, and I have these dots, these ellipses, because it was way too long to put on the overview sheet, but I at least wanted to give you a sense of how to start. So the last thing we're going to talk about is limitations of the Schwarz Christoffel transformation. The thing about the Schwarz Christoffel transformation is that it's written in terms of these x sub i's over here on the real axis, not in terms of the wi, which are their images. You know, if it were in terms of the wi's, that would be super, but they're not. So no more than 3 of these points, these x sub i's, can be chosen arbitrarily. So we had chosen, you know, -1 and 1 in our triangle example, but no more than 3 can be chosen arbitrarily. The others have to be solved for. So when the given polygon has more than 3 sides, some of the points x sub j must be determined in order to make the given polygon, or any polygon similar to it, to be the image of the x-axis. Often the integral cannot be evaluated in terms of a finite number of elementary functions. You notice how we use the beta function. There are cases where the solution of the problems by means of the transformation can become quite involved. To review what we have gone over, we looked at the Schwarz Christoffel transformation, which is a mapping W equals f of z that maps the entire x-axis in the complex plane, so the real axis, onto a polygon of n sides over here. So x1, x2, x3 up to xn minus 1 and xn equals infinity, those are the points on the real axis, are the points on the axis whose images then are the vertices of the polygon. Also these x1, x2, we write them in increasing order from left to right. The vertices of the polygon are then the endpoints f of x1, x2, up to xn, or wj is equal to f of xj, where j is the 1 to up to n minus 1, and wn is equal to f of infinity. And the function f should be such that the argument of f prime of z, so we started by talking about how f prime of z should look. So the argument of f prime of z should jump from one constant value to another, and at the points z equals x sub j. So in other words, the derivative or how the argument changes should be constant until we hit a point, a vertice point. Then what we have is, once we have this f prime of z, we did the integral in order to get f of z. So then our Schwarz Christoffel transformation is w equals f of z, which is the integral of a, we pulled out our constant a, z naught to z of s minus x1 to the minus k1, s minus x2 to the minus k2, all the way up to s minus x of n to the minus kn minus 1. And what we have is these k1, k2 up to kn minus 1. When we multiply by pi, that gives us the angle that we need to rotate by at each vertice. We have some other notes that our k values sum to 2 with some derivation here. Also, a couple of notes. We can choose a to be equal to 1 since a is a scaling function, and b over here, which is our constant of integration, since it is a translation, we can choose b equal to 0, and the resulting polygon will be a polygon p prime, but it'll be similar to the polygon that we were trying to model. It'll just be off by a scaling factor and a translation. We have this expression here that we used for our examples, and then we also used the beta function for some of our integrals. So when we got our integrals in this form, we just said we left it as b of p and q. We did the example of the equilateral triangle, which was much more complicated or had many more steps, hence the ellipses, and we talked about the limitations of the Schwarz Christoffel transformation. So that wraps up this video. Thank you for watching.